Use the product rule to expand the logarithmic expression. Whenever possible, evaluate the logarithmic expressions. This expression is log base 2 of 16x. The directions do specify to use the product rule, so let's write down what the product rule is. Product rule deals with having a product inside a logarithm. So let's say we have log base b of m times n. The product rule can be used to expand the logarithmic expression instead of into this one log into multiple logs. So what we have is that multiplication inside the log, and that first factor will go inside the first log, and the second factor will go inside the second log. And then because we have the product inside the log, we're going to add those logs together. So this is expanding with the product rule. Log base b of m times n is equal to log base b of m plus log base b of n. So in this example, we have a product inside the log. We have 16x. So we can write this as log base 2 of 16 plus log base 2 of x. And then in the second sentence it says, whenever possible, we want to evaluate. So anytime we have the log of a number, we want to try to evaluate that log. So on the side here, I'm going to work out what log base 2 of 16 is. So since I'm not sure initially, I'm going to say that this is equal to some p. I'm going to use the definition of what a log is to rewrite it in exponential form. Logs and exponents are inverses of each other, and so we can write equivalent expressions for those. So the equivalent exponential expression would use a base of 2. The log always equals the exponent, so we'll use a power of p. And then my expression will equal what's inside the log, so that's going to equal 16. 2 to the p equals 16. Now that it's in exponential form, I can think about that I know that 2 to the second power is 4, 2 to the third power is 8, and then 2 to the fourth power is 16. So since 2 to the fourth power is 16, I know that p is 4, and log base 2 of 16 is 4. So this gives 4 plus log base 2 of x for my simplified expression, or my expanded expression. Solve the logarithmic equation. Log base 3 of 5x minus 8 equals 2. So in this log equation, I have log only on one side of the equation. So I'm going to use a method that is to convert this to an exponential equation. Before we do this example, I really keep in my back pocket two main methods for solving log equations. And one of them involves when you have y equals log base b of x. So that's if you have log only on one side. And the other one is when you have log base b of m equals log base b of n. So logs on both sides. So when I have log only on one side, I'm going to convert to an exponential. That's b to the y equals x. That's the equivalent exponential form. And when I have logs on both sides, you have to make sure that they have the same base, otherwise this is not going to work. And what you can do is you can say what's inside the logs have to be equal to each other. So these are the two strategies that I keep in mind, and this example has log only on one side, so we're going to use the strategy of converting to an exponential. So converting to an exponential would mean that I have a base of 3. The log always equals the exponent. So we have an exponent of 2. And then this expression equals what's inside the log. That's 5x minus 8. So we get the equation 3 squared, which is 9, equals 5x minus 8. I can solve this by getting x by itself. I'm going to add 8 to both sides. That gives 17 equals 5x. I'll continue solving, getting x by itself by dividing by 5, and I get x equals 17 over 5. Now with every log equation, you should check to make sure that the answer that you came up with is in the domain of the original log expression. So I'm going to substitute this 17 over 5 into log base 3 of 5x minus 8. So that's 5 times 17 over 5 minus 8 equals 2. And what I'm checking for, remember, I'm checking to see if this value of x is in the domain. For logarithms, you can only take the log of positive values. The log of a negative is undefined, the log of 0 is undefined. So I need this expression that's inside the log to be positive. And I can see that it is. These 5's would cancel out, and I would have 17 minus 8. That's equal to 9. And I'm taking the log of a positive. So 17 over 5 would be in the domain of this expression. So we're going to be able to keep that solution. So the solution to this log equation is 17 over 5. On this question, we want to solve the logarithmic equation. Log of 9 minus 5x equals 1. So when I'm solving a logarithmic equation, I want to pay attention to whether I have log on one side of the equation or log on both sides. This one has log only on one side, so I'm going to use the method of converting to an exponential. So that's using the definition of a log. You have y equals log base b of x. We can convert that using the definition, convert it to an exponential. That would be b to the y equals x. Now on this example, we notice that we don't have a base that's specified like we usually do. And whenever we have a situation like this, we're using our special notation, and log with no base specified means log base 10. So log of 9 minus 5x is the same thing as log base 10 of 9 minus 5x. So let's rewrite our equation in that way. We have log base 10 of 9 minus 5x equals 1. Then I'm going to convert this to an exponential following the definition that we have over here. The base of the log is going to be the base of the exponential. The log always equals the exponent, so since this log equals 1, the exponent will be 1. And this expression will equal whatever is inside the logarithm. So inside the log, I have 9 minus 5x. So this expression equals 9 minus 5x. Now I'm going to try to solve the equation that I have now. 10 to the first power is 10. So I have 10 equals 9 minus 5x. I'm going to solve for x by subtracting 9 on both sides. That gives 10 minus 9 is 1 equals negative 5x, and I'll divide both sides by negative 5, giving me a solution of negative 1/5. But with every log equation, you need to check to make sure that your solution is in the domain of the log expression that you have. So I'm going to check x equals -1/5 by substituting it into the original equation. That's log of 9 minus 5 times -1/5 equals 1. And if I were to simplify this, I have a negative or a minus and a negative. Those will simplify to be a positive. That's 9 plus 5 times 1/5 equals 1. And I can see that what's inside the log is going to be positive. Now we can take the log of positive numbers. The log of negative numbers is undefined. The log of 0 is undefined. So we're going to, because we have the log of a positive, we're going to be able to keep that solution of x equals -1/5. So that is the solution to our log equation. We want to solve the logarithmic equation, log base 2 of 5 minus x. Excuse me, I misspoke there. Log base 2 of 5x minus 4 equals -2. So we're going to solve this log equation, and we notice once again that we have log only on one side of the equation. So when we have log only on one side, we're going to solve using the method of converting or using the definition of a log. So for the definition of a log, we have log base b of x equals y. We can write this log equation as an exponential b to the y equals x. And so we're going to write this in our exponential form. We have a base of 2, and that's going to be the base of our exponential. The log always equals the exponent, so we're going to have an exponent of -2. And this expression will equal the expression inside the logarithm, so that's 5x minus 4. So we've converted this log equation to the exponential equation of 2 to the -1 equals 5x minus 4. So I'm going to simplify this equation. On the left-hand side, I have 2 to the -2. That's the same thing as 1 over 2 squared. So that negative in the exponent gives us the reciprocal. And 2 squared is 4. So we have 1/4 equals 5x minus 4. And I'll solve this by getting x by itself. So I'm going to add 4 to both sides. 5x equals, in order to add these together, we need to have a common denominator. So 4 is the same thing as 4 over 1. And I need that to have a denominator of 4. So I'm going to multiply by 4 over 4. That's going to give 16 over 4. So 1/4 plus 16 over 4 is 17 over 4. We have 17 over 4 equals 5x. And I want to get x by itself, so I'll divide both sides by 5. I have x equals 17 over 4 divided by 5. When we divide fractions, we multiply by the reciprocal. That's 17 over 4 times 1/5. And we'll multiply straight across and get 17 over 20 as our solution. We do need to check to make sure that our answer is in the domain of the log. Logarithms have restricted domains. We can take the log of only positive values. So I'm going to check to make sure that this 17 over 20 is in the domain. We have log base 2 of 5 times 17 over 20 minus 4 equals -2. The 5 and the 20 will cancel each other out. So 5 goes into 24 times, and we would have log base 2 of 17 over 4 minus 4. And I need a common denominator. That will be 16 over 4. 17 over 4 minus 16 over 4 is 1/4, and that is a positive value. So that means that 17 over 20 is in the domain because it creates that positive value inside the logarithm. So we're going to be able to keep that solution of 17 over 20. On this question, we want to solve the logarithmic equation log base x of 5 equals -1. So on this question, we have log only on one side of the equation. So we're going to solve this by converting to an exponential. So if we have y equals log base b of x, we can convert that to an exponential using the definition b to the y equals x. So if we're converting this, we would have a base of x. The log always equals the exponent. So we have an exponent of -1. And this expression will equal what's inside the log, which is 5. So we have x to the -1 equals 5. Let's write this without the colors. X to the -1 equals 5. X to the -1 is the same thing as 1 over x. When we have a negative in the exponent, that's using the reciprocal of the base. So if we want to apply the negative, we need to do the reciprocal of the base. I can solve this by multiplying by x on both sides. That's called clearing fractions. That gives me 1 equals 5x. And I can solve for x by dividing by 5 on both sides, and we have x is equal to 1/5. Now this is an interesting example because our variable is in the base, and we have some specific rules about the base. The base is allowed to be positive and also not equal to 1. So these are the restrictions that we have for the base. And since 1/5 is positive or greater than 0 and also not equal to 1, this is a base that is allowed with logarithms. So we have x equals 1/5. We're going to solve the logarithmic equation and be sure to reject any value of x that is not in the domain of the original logarithmic expression. The equation that we're working with on this one is 3 ln of 8x equals 9. So we notice that we only have a log on one side of the equation, and so we're going to use that method of converting to an exponential. So remember, if we have y equals log base b of x, we can convert that to an exponential using the definition, and that would be b to the y equals x. Now, we have a couple things in our way this time, and the first thing I notice is that I have a coefficient on the logarithm. So I can't convert the equation yet because the log isn't isolated on one side of the equation. So I need to get rid of that 3. And I can think of two different ways to get rid of that 3. I'd like to show you both of them. So one way would be, I'm going to rewrite the equation twice to show you both ways. So one way would be to divide by 3 on both sides. That would give natural log of 8x equals 3. The other way to get rid of that 3 would be to use one of our log properties And one of our log properties says that if we have a coefficient, we can move that into the exponent. So that would give natural log of 8x to the third power equals 9. So then our next obstacle that we have here is that most of our logs are written in this way here, log base b. Well, this log is written with a special notation with ln, which stands for natural log. So ln of, let's say, some m, what that means is log base e of m. So e is our special base, we call it the natural base, and so logs with that natural base are called natural logs, and we use this special notation. So we have to keep in mind that this equation actually means log base e of 8x equals 3. Or this one over here, log base e of 8x cubed equals 9. So once we understand that, we can convert our log equation into an exponential equation. So we're going to use the base of e. The log always equals the exponent. And then inside of our log is 8x, and that's what our expression equals. So we have e to the third equals 8x. Now on the other one, we would also convert using a base of e. The log equals the exponent, so we have 9. And this will equal what's inside of the logarithm, which is 8x cubed. Now in order to solve this equation, we want to get x by itself. So on the left-hand side, I would divide both sides by 8 and get x equals e to the third over 8. On the right-hand side, we have a little bit of extra solving to do. I have to get rid of that cube. To do that, I would cube root both sides. That's cube root of e to the ninth equals cube root of 8x cubed. The cube root and the cube cancel each other out, giving you 8x. On the left-hand side, we have to simplify that radical. And if you don't remember the details of how to do that, one strategy that you could do is rewrite that radical as an exponent. So that would be e to the ninth to the 1/3 power. And then you can multiply those powers together and it becomes e cubed. And you can see here we're in the same state as the other equation. We can divide both sides by 8 and get x equals e cubed over 8. So both strategies for solving this got us to x equals e cubed. And I want to check to make sure that this is in the domain. So we're checking to see if e cubed over 8 is in the domain. So we substitute that in. We get natural log of 8 times e cubed over 8. And that equals 9. The 8's cancel. And so inside the log, we have e cubed. And this is a positive number. E is approximately 2.718. And if we take a positive number and raise it to the third power, it will still be positive. So e cubed over 8 is in the domain of this logarithmic expression. So that is our solution, e cubed over 8. Now on this example, we want to solve the exponential equation 15 to the 3x plus 1 equals 7 to the x minus 3. Now, with exponential equations, there are three main methods that I keep in my back pocket for solving exponential equations. So the three methods are: one, we try to make the bases the same. We try to get the equation to a format where we have b to the m power equals b to the n power. If we're able to get the equation to a state like this, then we can simplify by saying that the exponents must be equal to each other. This is using a one-to-one property of exponentials. The book that I'm using right now calls this relating the bases. The second way, so if I can't do it that first way, then I try to convert the exponential equation into a log equation. So I'll start off with some exponential equation, y equals b to the x. I can convert that to a log equation using the definition of logs. That would be log base b of y equals x. And this works on most exponential equations. And the third way, which also works on most exponential equations, is if you start off with an exponential equation, you can apply the log to both sides of the equation. So that would give natural log of y on the left-hand side of the equation, natural log of b to the x, applying the natural log to the right-hand side of the equation. Now, the advantage of having a log in your equation is that once you have that log in the equation, you get all of the nice properties that come with logarithms. You get the power rule, the quotient rule, the product rule, specifically the power rule, because the power rule allows you to take this out of the exponent and put it into the coefficient of the log. So that's really helpful in solving the exponential equations because the variable gets moved out of the exponent. So looking at our example, I can see that my first option of making the bases the same is not going to work. We have a base of 15 and a base of 7, so I'm not going to be able to write the equation so that the bases are the same on both sides. So that method is out. But I can use either one of the other two methods to solve this. So my preference is to use this method here of taking the log of both sides. And my reason behind that is because even though the answer might look a little cleaner, in the second method, the answer looks cleaner. So less symbols, less logarithms using that second method. However, most of your problems are going to ask you to type your answer in a calculator. And if you're typing it in a calculator, you might be forced to use only log base 10 or natural log. And so this method number 3 that I have here is going to make sure that our answer is using only natural logs, and that's going to be more convenient for typing it into the calculator. So I'm going to use that third method to work this out the first time. We'll put it into the calculator, and then I'll come back and I'll do it with the other method. So I'll show you it's possible to do both. So on this example, I'm going to apply the natural log to both sides. We have natural log of 15 to the 3x plus 1 equals natural log of 7 to the x minus 3. Then we're going to apply the power rule for logarithms on each side. So that would give the equation 3x plus 1 natural log of 15 equals x minus 3 natural log of 7. Next, I'm going to get rid of these parentheses using the distributive property. So I'm going to distribute the natural log of 15 to both terms, and I'm going to distribute the natural log of 7 to both terms. So this gives 3x natural log of 15 plus natural log of 15 equals x natural log of 7 minus 3 natural log of 7. So I've gotten rid of the variable and the exponent, I've gotten rid of the parentheses, and now I'm ready to solve for x. So what I notice is that I've got x in two different terms, one on the left-hand side of the equation, one on the right-hand side. I want to collect those x's onto the same side. So I'm going to move this variable term to the left-hand side of the equation so that they're on the same side. Then I also notice that I have two terms without variables. We call those constants. And I want to collect those terms together onto the other side of the equation. So I want to move this natural log of 15 to the right-hand side. So rearranging the terms in that way, I would have 3x natural log of 15 plus, sorry, that should be a minus, minus x natural log of 7, and that equals a negative natural log of 15 minus 3 natural log of 7. And now that I've collected those x's onto the same side, I can factor out the x from both of those terms, and that would leave me with 3 natural log of 15 minus natural log of 7. On the right-hand side, I'm not going to do anything except for just copy down what I already have. And then finally, I can solve for x by dividing both sides by what's in the parenthesis. So I'm dividing both sides by 3 natural log of 15 minus natural log of 7. So I've got my solution, and that's x equals negative natural log of 15 minus 3 natural log of 7 divided by 3 natural log of 15 minus natural log of 7. So as I said, this method is the one that I prefer because of the calculator only. So I'm going to pull up my calculator so that we can type this expression in. So it's loading right now. And then we'll come back and we'll do this problem with the other method. So here's the calculator that I'm using. And I want to type that expression that you see below into this calculator. Now, in this expression, we've got multiple terms in the numerator and multiple terms in the denominator. So I've got to make sure that I follow order of operations. So I'm going to put parentheses around the numerator. So I've got negative ln of 15 minus 3 ln of 7. And I need to close parentheses for the whole numerator. And I'm also putting parentheses around the denominator, so that would be 3 natural log of 15 minus natural log of 7. And I'm closing parentheses for the denominator as well. So we've got negative 1 point, let's round to 2 decimal places, that would be negative 1.11. Okay, so I want to show you the other method. We have 15 to the 3x plus 1 equals 7 to the x minus 3. So if I'm going to use the second method there to convert this to a log, I'm going to have to decide which base I want to use. So I can either use a base of 15 or I can use a base of 7. I'll use a base of 15. So that would give me log base 15. The log always equals the exponent. So I want to make sure that I use the exponent that is on the base that I chose to use. So if I used a base of 7, the exponent would be x minus 3. The log would equal x minus 3. But since I chose a base of 15, I want to use the exponent of 3x plus 1. And then inside the log will be the 7 to the x minus 3. So we've converted this to a log equation. And then it's going to be very similar to what we saw on this other method. I'm going to use the power rule to get that variable out of the exponent. So I would have x minus 3 times log base 15 of 7 equals 3x plus 1. I would use the distributive property to get rid of those parentheses. And that gives x log base 15 of 7 minus 3 log base 15 of 7 equals 3x plus 1. And just like on the other example, I have gotten the variable out of the exponent. I have used the distributive property to get rid of the parentheses. And now I'm paying attention to, I have multiple variable terms, which I want them on the same side. So I'll move this 3x to the left so that the variables can be collected on one side. I have two constant terms. I want those on the other side of the equation. We can factor the x out, or sorry, we want to rearrange the terms. We have x log base 15 of 7 minus 3x equals 1 plus 3 log base 15 of 7. I can now factor that x out. Log base 15 of 7 minus 3 equals 1 plus 3 log base 15 of 7. And now I can get x by itself by dividing both sides by the parentheses. That would give 1 plus 3 log base 15 of 7 over log base 15 of 7 minus 3. So the answer looks a little bit cleaner. We have less logs in it. But on this particular calculator, you can only do log base 10 and log base E on the home screen. In a hidden menu, we do have this log base, which allows me to specify the base. So I will be able to do log base 15 of 7. However, not all calculators have this function that allows you to type the base. So let's type this one in to make sure we get the same answer. We're going to put parentheses around our whole numerator. That's 1 plus 3. And we need that function in the hidden menu. We have log base 15 of 7. And I need to close parenthesis for that whole numerator. Then I'm going to divide. And I'm going to do log, oops, I need the special one. So math, go up to get to the bottom of the list. It's log base 15 of 7 minus 3, and we'll close parenthesis for the whole denominator. And it looks like I got a different answer. So let me think for a second about whether I made a mistake here. Okay, I'm not seeing it right away, so I'm going to pause to take a closer look. Okay, so after looking for a couple moments, I noticed that when I typed the first way I solved it, I left off a parenthesis after this 15. So you have to be really, really careful about making sure you close parenthesis for the log and close parenthesis for the denominator as well. So let's insert here parenthesis, and now we have the two answers matching each other. So our correct one is negative 1.38. So let's correct this, negative 1.38. Okay, so we've got our two different methods there for solving the log equation, and a really great reminder about being careful with the parentheses when we type into the calculator. On this question, we want to solve the logarithmic equation. We want to make sure that we reject any value of x that is not in the domain of the original expression. So this one, I notice that I have log only on one side of the equation. So I'm going to solve this by converting it to an exponential. So if we have a log equation, y equals log base b of x, we can have the equivalent exponential equation, which is b to the y equals x. But we notice that we have this 8 in front of the log. So we are not in the right format to be able to convert. We need to get rid of that 8. And there are two different ways that we can get rid of that 8. So I'm going to copy the equation down so that we can look at both ways. So one way to get rid of that 8 would be to divide both sides by 8. And that gives natural log of 6x equals 3. The other way to get rid of that 8 is to use one of our properties of logarithms, which is called the power rule. And we can move that 8 into the power using that power rule. So that would give natural log of 6x to the 8th equals 24. So now that we have that 8 off the coefficient, we can convert this to an exponential equation. We are using some special symbols in this example. We're using ln instead of log, so we have to keep in mind what those special symbols mean. Natural log of m is the same thing as log base e of m. So ln stands for natural log. E is the natural base. So we have that special symbol. So we have to keep in mind that this is log base e of 6x equals 3. Log base e of 6x to the 8th equals 24. Then we can convert this to an exponential, and that would give e to the 3rd equals 6x. E to the 24 equals 6x to the 8th. With the equation on the left, we're almost done solving. We would divide by 6, and x equals e to the 3rd over 6. We would just need to check to make sure that this is in the domain. And we can see that if we substitute in for this x, e is positive, e cubed is positive, dividing by 6 is still positive, and multiplying by 6 is still positive. So e to the third over 6 is in the domain and can be used as a solution to this equation. We have a little bit more work to do on the other version of the equation. I'll have to get rid of that 8th power, and I can do that by taking the 8th root on both sides. So I'm doing the 8th root of 24 on the left and the 8th root of 6x to the 8th on the right. When I do the 8th root of something to the 8th, those cancel out and get me 6x. But because these are even powers, I'm going to get a plus or minus on the other side of the equation. The 8th root of e to the 24th will be e to the third power. And we know that because 8 goes into that power of 24 3 times. So finally, we can get x by itself by dividing by 6 on both sides, and we have x equals plus and minus e to the third over 6. We've already checked the positive e to the third over 6. So let's check the negative. So if I have 8 natural log of 6 times a negative e cubed over 6 equals 24, we have a negative number dividing by a positive is still negative, multiplying by positive is still negative, so that's going to give a negative inside of our logarithm. So x equals positive e cubed over 6 is our solution. The negative e over e cubed over 6 has to be excluded. In this question, we want to solve the logarithmic equation, reject any values of x that are not in the domain, and we want to give the exact answer. The exact answer is going to involve logs or exponentials, and then we want to use a calculator to give the approximation. So in this example, I'm noticing that I have log on one side of the equation. So I'm going to use the method of converting. So when we have the format of y equals log base b of x, I can convert that to an exponential using the definition, and that would be b to the y equals x. I do have a couple issues here in that in my definition, log is the only thing on one side of the equation. So I need to get this equation so that the log is isolated first. So I would subtract 8 on both sides, and that would give 3 natural log of x equals negative 1. Then I would divide by 3 on both sides and get natural log of x equals negative 1/3. So now I've got the log isolated, so I can convert this. But I also notice that I'm using special symbols. I usually have log with a base that's specified. Here I have ln. So this is something that I have to have memorized, that the symbols ln, let's say ln of m, actually mean log base e of m. So let's rewrite it with that format. This is log base e of x equals negative 1/3. Now we can write this as an exponential equation. We're going to use the base of e, the exponent of negative 1/3, equals what's inside the log, which is x. So we have our solution here. The exact answer is x equals e to the negative 1/3. We also want the approximation, and we want that approximation to 2 decimal places, so let's get our calculator. And in our calculator, we're going to type e to the negative 1/3. So we've got e right here, which is above the ln button. So I'll hit second ln to get e to a power. And in that power, I have negative 1/3. So that is rounded to 2 decimal place, going to be 0.72. And getting the decimal approximation sees that if I substituted this in for x, I would be taking the log of a positive, and I can keep this solution of e to the negative 1/3 or 0.72 as the solution.
Thank you for checking out my videos. Have a great day.